Today we're going to learn how to solve systems of three variable equations algebraically. So the first thing we need to discuss is the different types of solutions you can get for a three variable system. So one of the options is a one solution. This means that three planes will intersect at one point. And this happens when you get a value for x, y, and z. To get infinite solutions, this is where all three planes intersect at a line rather than at one point. You have two equal sides of the equation that are always equal, such as 0 equals 0 or -5 equals -5. No solution is when the planes don't ever all intersect at the same point, or when you get a false equation. For example, 0 equals 2. Or when you have two inconsistent y values, meaning that if I substitute a value in, I get one value for y, but if I substitute it into a different equation, I'm going to get a different value for y. So with that being said, we're going to start off by trying to solve this first system of equations. So in solving this three variable system of equations, I'm typically going to use mostly elimination and probably only a little bit of substitution. So the first thing I'm actually going to do is, in this case, if I look at my first equation and my second equation, I have a 2z and a negative z. So actually the first thing I'm going to do is eliminate z. And I'm going to do that by taking that second equation and I'm going to multiply it by 2. So I'm going to get 3x plus 4y plus 2z equals 11. That's the first equation that's not changing. Now, if I multiply the second equation by 2, I'm going to get 4x plus 6y minus 2z equals 8. So when I go to add these two equations together, my z's are actually going to eliminate. So I'll be left with 7x plus 10y equals 19. Now, I would like to have a second equation where I also eliminate z. So now I'm going to look at my second equation and my third equation. So in my third equation, I have a negative 3z. And in my second equation, again, I have that negative z. So now when I add those two together, I want z to also eliminate. So instead of multiplying the second equation by 2 this time, I'm actually going to multiply it by a negative 3. So that means when I multiply that equation by negative 3, I'm going to get negative 6x minus 9y plus 3z. And that's going to equal negative 12. And then my last equation is actually going to stay the same. Now when I add these two equations together, I'll get negative 1x or negative x minus 4y equals negative 13. And again, my z's are going to eliminate, which is good because now I have two variable systems of equations. So now I'm going to take my two variable systems of equations and I'm going to stack these. So I'm going to have 7x plus 10y equals 19. And I'm going to have negative x minus 4y equals negative 13. And now I want to use elimination another time, or I could do substitution, but I basically want to solve for x or y in this case. So what I'm going to do is I see I have a 7x and I have a negative x. So I'm actually going to multiply this second equation by 7. And that's going to give me negative 7x minus 28y equals negative 91. And then I'm actually just going to take that top equation and bring it down underneath. 7x plus 10y equals 19. Now, if I add these two equations together, the x's will eliminate and I'll get negative 18y equals negative 72. So y will actually equal 4. So now that I've solved for y, or just one of my variables, I need to go back and use either of my two variable equations to now find x. So I'm going to use this first equation here. So I'm going to use 7x plus 10y equals 19. And I'm going to substitute that 4 in for y, so that way I can solve for x. And I'll get that x is -3. Now that I have two variables, I'm going to pick one of my original equations and substitute in -3 for x and 4 for y in order to find z. So I'm actually just going to use the first equation. So I'm going to use the first equation, which was 3x plus 4y plus 2z equals 11. I'm going to substitute in -3 for x and 4 for y, and then I'm going to solve for z. So I'm going to have -9 plus 16 plus 2z equals 11. I'm going to have 7 plus 2z equals 11. And I'm going to end up getting that z equals 2. So my final answer will be that a ordered triple of -3, 4, and 2, because my ordered triple I will always write as x, y, z. So number 1 is an example of a system with one solution. Now we're going to go through examples 2 and 3, which will give us some examples of what a infinite solutions or a no solution could look like. So when looking at number 2, the first thing I notice is when I look at my first two equations, that if I were to actually subtract my first two equations, both x and z would eliminate. So right away, I can kind of see that something unusual is going to happen. So I'm going to subtract these two equations. So x minus x, well, that will eliminate x. -2y minus y will give me a -3y. Z minus z, well, z will also eliminate. And then 4 minus 2 is 2. So I'm going to get that y equals -2/3. Now, I only have one variable, so I still need to find a way basically to eliminate another variable in order to solve for either y or z. Because right now, this doesn't show me that I'm going to have a special solution, because I did get a solution for y. So now, using my first equation again, and now my third equation, I'm going to actually multiply my first equation by -3. So that way, my x's or my z's will eliminate as well. So if I multiply my first equation by -3, I will get -3x plus 6y minus 3z equals -12. And then I'm going to add that to the third equation that's unchanged, which would be 3x plus 3y plus 3z equals 14. Now, when I go to add these two equations together, my x's will eliminate. I will get 9y. My z's will eliminate, and it will be equal to 2, which means I'm going to get y equals 9/2. Well, from before, I got y equals -2/3, and now I'm getting y equals 2/9. So this is one of the signs that if I get inconsistent values for a variable, that means that this three-variable system has no solution. Meaning that all three of these planes do not intersect at one point. All right, so finally I'm going to look at this last equation. And as I look at this last equation, it's actually perfectly already set up to eliminate z. So if I look at the first two equations, and I start off by adding those two together, so I'm going to do the first equation and the second equation. And if I add those together, my z is going to eliminate. So I'm going to add those two together to get a new equation. And I'm going to get 2x plus 4y equals 4. Then I'm going to do the same thing, but I'm going to do the second equation and the third equation. So I'm going to have x plus y minus z equals 2, and 2x plus 2y plus z equals 4. Now I'm going to add these two equations together, and my z's will eliminate, and I will get 3x plus 3y equals 6. Now I'm going to stack these two equations. So I'm going to have 2x plus 4y equals 4. Oh, excuse me, I made a mistake. This should have been a 2y. I apologize. So 2x plus 2y. And then I have 3x plus 3y equals 6. Now, I want to eliminate one of my variables. So let's say I'm going to eliminate x. To eliminate x, I am going to multiply this top equation by 3 and multiply this bottom equation by -2. So that will give me 6x plus 6y equals 12, and -6x minus 6y equals -12. And what's going to happen is actually x and y are both going to eliminate, and I'm going to get 0 equals 0. Well, that's a true statement. So since it's a true statement, that means there's actually infinitely many solutions. Because these three equations don't just meet at one point, they actually meet along a line. And so that way there's infinitely many solutions rather than just one solution. So we went over the 3 different types of solutions we could have: infinitely many, no solution, as well as one solution. Now you're going to give these a try and practice solving 3x3 systems.